All right, let's get right into it. For the longest time, teaching a computer to see was just a slog, a really slow, painful process. You'd have to feed it millions of pictures of a cat just so it could learn what a cat looks like. But what if? What if an AI could learn to see not from these perfectly labeled photos, but by just reading the internet? Today, we're breaking down Clip, a model that completely changed the game by doing exactly that. So here's how we're going to do it. First, we'll tackle the massive problem that AI vision systems were stuck on for years. Then, we'll see how Clip's creators used language to completely flip the script, unlocking this incredible superpower called zero-shot learning. But, and this is important, this power isn't perfect. We're also going to explore how it comes with some very, very human flaws. Okay, so let's set the stage here. The big challenge, the real bottleneck in computer vision, has always been how we teach these models in the first place. And the old way? It was incredibly rigid. Just think about this for a second. If you're building an AI from the ground up to spot these three simple things, what's the one ingredient you absolutely need? The answer is data. But not just any data. You need a mountain of very specific hand-labeled data. And this slide just lays it out perfectly. The old way versus the new idea. So traditionally, if you wanted an AI to find cats, you had to go out and get this giant data set of images, where every single one was carefully labeled cat. Now here's the crazy part. If you then decided you wanted it to recognize dogs, well, too bad. You had to start all over again from scratch with a whole new data set for dogs. It was brittle, it was slow, and it was ridiculously expensive. So the new idea, the one that sparked Clip, was this. What if we could just let the AI learn from all the messy, natural text that people already write to describe images all across the internet? It's a brilliant thought, but the million-dollar question was, could that possibly work? And that brings us to Clip's totally radical solution. Instead of teaching an AI what a cat is, they decided to teach it to simply connect the image of a cat with the words "a photo of a cat." Simple, right? But it changes everything. So the fancy term for this is contrastive learning, but honestly, you can just think of it as a giant, massive matching game. The AI gets a huge pile of images and a huge pile of text captions, all shuffled up. Its only job, its entire goal, is to figure out which picture goes with which description. It doesn't actually need to know what a dog is in the philosophical sense. It just needs to learn that this specific image is the best possible match for the text, "a photo of a dog." And to play a game this big, you need a truly massive playground. We're talking about a dataset of 400 million image and text pairs that the researchers scraped from all over the internet. That's not a typo. 400 million. By playing this matching game over and over and over, the AI started to build this intuitive understanding of what concepts actually look like. So here's how it all comes together in 3 simple steps. First, there's the pre-training. That's the big matching game with the 400 million pairs. What this does is create this kind of internal map, a shared space where the idea of a dog in a picture is right next to the text for dog. Step 2, when you want to give it a new job, you don't show it more pictures. This is the crazy part. You just give it text prompts like a photo of a dog or a photo of a cat. And finally, for the prediction, you show it a brand new image it's never seen before, and the AI just looks at its internal map and figures out which of your text prompts is the closest match. That's it. And this is what unlocks Clip's real superpower, something called zero-shot transfer. It's the ability to do a task it was never, ever explicitly trained on, using literally 0 new examples. Let's just walk through a super quick example. We show Clip a picture of a dog. Now, remember, it has not been trained on some clean data set specifically labeled dog. Then we ask it, hey, pick between these 2 text descriptions, a photo of a cat or a photo of a dog. And no surprise, it nails it. It correctly says the best match is a photo of a dog. But here's where it gets really, really cool. We can give it much more nuanced options, like a drawing of a dog versus a photo of a dog. And it's smart enough to figure out that a photo of a dog is the more accurate description. This kind of flexibility is what makes it so powerful. It's not just matching rigid labels, it's understanding concepts. And this quote from the researchers themselves just sums it all up. They found that Clip, without seeing a single one of the 1.28 million labeled images from the famous ImageNet benchmark, could match the performance of a top-tier model that was trained on all of it. This wasn't just a step forward. This was a game changer. Okay, so it sounds like magic, but how good is it really? I mean, matching one model is impressive, But let's actually look at the numbers and see how it stacks up. I mean, just look at this chart. The scale of the improvement is just staggering. Zero-shot clip hits 76.2% accuracy on ImageNet, which is the exact same as a fully supervised model. But now look at the previous best for zero-shot. It was only at 11.5%. So Clip didn't just nudge the field forward, it launched it into a whole new orbit. And it's not just about raw accuracy. Clip is also way more robust. See, because it learned from the messy, chaotic, weird internet, it doesn't get easily fooled by strange images. A traditional model that's only ever seen perfect photos can get totally confused by a cartoon or a sketch, but Clip, it's seen all kinds of weird stuff online, so it handles them much, much better. But, and this is a huge but, that same messy, chaotic internet that makes Clip so strong also comes with some serious, unavoidable baggage. When an AI learns from unfiltered data created by humans, it doesn't just learn about cats and dogs. It also learns about our biases, our stereotypes, and our worst flaws. The problem is that Clip's incredible flexibility is a double-edged sword. It can be prompted to classify people into really sensitive or even harmful categories. And because all of its knowledge comes from us, it has learned to connect certain concepts in ways that mirror the deep-seated biases floating around in its training data. The researchers actually tested this directly. They gave the model images of people from a standard dataset and asked it to classify them against a list that included crime-related labels. The results showed some really significant and disturbing disparities. As you can see, some groups were far more likely to be misclassified into these harmful categories than others, which is a direct reflection of dangerous stereotypes found online. And the researchers also found something else that was deeply troubling. The model misclassified 14% of images of Black people into non-human categories like gorilla or animal. That's nearly double the rate for other racial groups. This isn't just some random glitch. It's a direct mirror of some of the most toxic, racist content that exists in its training data. Which leaves us all with this really big, difficult question. Look, Clip is a monumental leap forward in how machines can learn to understand our world. But it also holds up a mirror to the world of data that we create. So as we build these unbelievably powerful systems, the challenge isn't just a technical one, it's an ethical one. When an AI learns from our collective digital footprint, how in the world do we teach it to be better than us?